Consider the following family of line segments on the coordinate plane. We take point 0 pi by 2 minus a and a comma 0 to be the endpoints of any line segment in the set for any a belonging to 0 to pi by 2. Let a be the union of all such lines, in fact all such line segments. We need to solve the problem. Let's get a feel of this problem and let's see what exactly problems demands from us. Okay, so they are talking about area A, so that's the keyword. And we have family of line segments. So first we need to comprehend why this represents a family. So as you can clearly see, we have 2 points. One is given as 0 comma pi by 2 minus a, and we have other point a comma 0. And since a is already changing from 0 to pi by 2, so the best thing that we can do is we can play with, like some line segment by keeping special values of a. So let's say if I keep a equals 0, so the point will become origin, and other point is 0 comma pi by 2. So we'll get line like this, right? If I'll keep a equals pi by 2, we'll get a horizontal line just slipping on the x-axis. For a value of a, let's say if I keep some 1, so clearly we'll have inclined line like this. For some other values, all these red guys will come. Okay, so just to save time, I have drawn the pictures. So this is just rough feel of. If we'll plot more and more values, like just a handwritten plot, you can clearly see it feels like there will be a net here, right? And it feels like we'll get some kind of envelope because the line cannot cross certain threshold values. Let me draw a live diagram for you. So we have line number 1, line 2. Maybe the other line, if I'll take the point, it'll slide over here. Other guy will go here. Guy will go here, and so on. So clearly you can see, like for some different situations, we'll have this array, and it feels like we have a cusp here, or some envelope of, like these lines. So let's pick up one of the sample line. And what I do is I write the equation of this line. And that's quite easy to write because the general equation of any line, that sample line is nothing. But we have got 2 points. Let's call it point A and point B. So in 2-point form, I just wrote the equation of line, right? Clearly this equation is satisfied for all A belonging to 0, pi by 2. So better now I'll call it a line segment. Now the question is how we can find the area of the region of this cusp. Okay, so there are 2 challenging things which we need to understand. One thing is how I'll show that each and every point in this region will be, like taken care of by these lines. So I am sure the union of all these lines will definitely create the entire continuous region. That's challenge number 1. The second challenge is if I can prove it will create that region, how to find the area of that. So clearly to find that we need to, like get the extreme boundary line of this curve. So we want at a particular x value, if I pick up a particular x0 value, there will be many lines passing through that. Like, so what is the maximum height that I can attain? So that's what I'm trying to find, the maximum height at a particular location, at a particular x0. Okay, so we have since family of lines. So in this family, let's say if I put x equals x0, depending upon a values, we'll have many lines. Okay, so at a particular locations, we'll have many lines, hence many y values, right? Out of all those y values, depending upon values of a, which is parameter, we want to maximize the height, because once I know maximum height at x0, I can change the height, I can change the location, let's say at x1, and I can find again maximum height there. I can change the location, let's say at 0.00001, and I can find the maximum height. So like this, at x equals 0, I already know the maximum height is pi by 2. So once I know the maximum height, the locus of maximum height will give me envelope. Okay. So I know the region, whatever region is, that cannot pass that. It cannot transpass. So I know at that maximum height, the locus of those maximum height will give, the boundary for that envelope. And just we need to find the area of this. So this is our thought process. And we go along that line. So keep x equals x0. We have y in terms of x0 and a. Clearly at a particular fixed location x0, we are trying to see the maximum height. So what is contributing in this height is a, because as a keep on changing, these lines will keep on changing, as I have explained, hence height will keep on changing. So to get y max is nothing but we'll differentiate with respect to a. So we want to search a line which will give me maximum height at that position, right? So just keeping dy by dA equals 0 will give a value as root pi x0 by 2. Again, it's all a's are nice in the sense like x0 itself is 0 to pi by 2. Because x0 is a location, because a is belonging to pi by 2. Okay, so all these x naught values, hence a values are valid. Now what's our plan? Our plan was try to find the function now, because once you know these maximum heights at every location, we'll try to find the locus of those maximum heights, right? And that locus will exactly give the uppermost boundary, and we know the lower boundary is bounded by x-axis and y-axis, so hence we can easily find the area of this just integrals, and that exactly have done. So at a particular x naught, we know the value of y is given by this. For maximum height, a equals will be root over pi x naught by 2, right? So since a is changing here, right, a is changing, so for a particular value of a and corresponding to x naught, we'll get maybe this point. Let's say a changes and the y value will get this, right? Again a changes, y value changes, so there will be definitely a value of a which is root over pi x naught by 2, at which we'll get the maximum height of this function. So in fact, if I were to write the equation of this, which is corresponding the boundary line, the boundary curve, so it will be y equals some function f of x which is attained at the maximum value of those height, right? Okay, so we need to find, you know, the maximum value of y corresponding to x naught. And how will you find it? Just put a equals root pi x naught by 2. So if we'll keep that, we'll get y equals this expression, which basically fundamentally boils down to y equals pi by 2 minus 2 root pi x naught by 2 plus x naught. As you can see, because these quantities will be just equal to this. Now what is x naught? You know, like x naught is particular location, and what is the significance of this y here? In fact, we are getting y max, right? So this is y max. Now y max versus x naught is basically giving the equation of that boundary. Okay, because for other point it will be y will be lesser than y max, and of course for equality will also. So we have an equation of that curve. Let's it's better to give a good familiar name to x naught usually, okay, just to make it more cool and more familiar with our notation of mathematical sense. Let's call it x. Hence the equation of that boundary is nothing but y equals pi by 2 minus 2 root pi by x plus 2 plus x. Now by doing so, we have already proved like each and every point on this graph is taken care of. Why? Because you see, like y will definitely be less than equal to y max, and since this is a continuous function, right, this is a continuous function, so at any particular value of x, the height that will be given by this equation will be the maximum height, y max. So you cannot surpass this height, right, because this point will not follow that union of lines. And all the points here on this line, all the points belonging to y to 0 to y max will be attained. Why? Because the function is continuous. All these points will be attained. All these points will be attained. It means there exists definitely at least one line, which will pass through any point in this region. So you give me any point on this region, definitely there is one line which will satisfy that conditions. Hence all the points in this region belongs to, as a is running from 0 to pi by 2, consist of all the point in the grid, consist of each and every points in the grid. And now we need to just calculate the area. Now what is area? Again we'll go by the Greek method. You know, you take a position x, take a snapshot of the small rectangular slice there. So the area of this small slice dA is going to be nothing but the function value into dx, so y dx. And now we need to swap this elastic membrane across this entire region from 0 to pi by 2. So that's how you integrate this. Okay, so it's basically this side is y into dx, so fx dx. So this is your small area, hence integration will be 0 to pi by 2 fx, which is rectangular height, and dx is the width. And if we integrate this, it's very simply we'll get pi square 24. So here is the answer to this beautiful problem. The area of that union of lines that you are getting is having pi connection, and that's kind of pi square 24. I hope you have enjoyed the problem, because usually, you know, like in JEE problem, they straightforward relate with ellipse and hyperbola and area bounded figures as well as sometimes circles. But this was a unique problem in its own, where the union of line is creating a region, and most importantly, I have given you a fundamental way of how to calculate the envelope of that line. On the same idea, many problems can still be posed. So my point was how to systematically develop your logical thinking and to conclude problems and enjoy problem solving. Okay, so if you liked it, please do like and subscribe and share among your friends for more quality content for free. Until then, bye bye, take care.